Now we're going to do the matrix of a reflection around the line y is equal to mx, but we're going to do this in steps. First, we're going to find out how to rotate something around the x-axis, and then we're going to find out how to flip something around the x-axis, reflect, and then we're going to find out how to rotate something by an angle theta, and then we're going to put them together, and that's what's going to give us our rotation matrix, our reflection matrix around the line y is equal to mx, which has everyone very intimidated. So the first thing is, if I have a vector and I want to reflect it across the x-axis, comes down here, this sends x1, x2 to negative to x1, negative x2, and so the matrix of this, I'm going to want a matrix which sends x1, x2, just intuitively, but technically the way I would do it is put in the e1s and e2s, but we'll get to that with linear transformations. I want a matrix that sends this to x1, negative x2, and this matrix, of course, will be 1, 0, 0, negative 1. Similarly, if I want to reflect something across the y-axis, I'm sending it to negative x1, x2, and the matrix that does this is negative 1, 0, 0, 1. But this is the one that we're going to be using to find out how to flip something across a line. But before we do that, we need to find out how to rotate something by an angle. So suppose I have this same line, or the same vector rather. A line is not a vector, a line goes on infinitely in both directions. A vector is a line segment, a directed line segment. And it makes an angle, say, theta, and I want to rotate it up. I want to rotate it counterclockwise by an angle, say, phi, here. Well,
I'd say phi, but okay.
No, it's phi.
It's phi.
It's actually phi.
It's phi.
You're actually wrong.
Let the record show that
Yeah,
it's
we're wrong.
pronounced
It's pronounced. I heard this. I had a Greek professor who went on a big rant about this. So now I say phi.
Yeah, so your phosphorus just take.
Yeah.
But phi's fine.
So what I want is, so first, in order to be able to do this, I'm going to come over here and we're going to have to discuss something called polar coordinates, which, if you haven't seen this before, if I have a vector with an x coordinate and a y coordinate, I draw a line down here, make a right angle. It has an angle theta, and this, of course, is the vertical distance y, this is the horizontal distance x, and I know that sine of theta is equal to y over this, we'll call this r, the length of the vector is equal to y over r, and cosine of theta is equal to x over r. And this gives me that x is equal to r cosine theta, and y is equal to r sine of theta. And so for the purposes of rotating a vector, we're just going to ignore the lengths. We're going to assume that they're 1, because it doesn't matter what the length of the vector is when you're rotating it, right? It just, the angle is what's important. So we're just going to be looking for a matrix that sends cosine theta, it's a horrible cosine theta, sine theta, to, what do we want? Cosine theta plus phi. We want it to make this angle, this big angle, which is theta plus phi afterwards. Cosine theta plus phi, sine theta plus phi. And this is where we need to remember our addition formulas for sine and cosine from high school, which is that cosine of theta plus phi is, of course, cosine theta cos phi minus sine theta sine phi, and sine theta plus phi is equal to sine theta cos phi plus sine phi cos theta. And so what I want, now I'll get rid of this to give myself some more space to read, or to write, is a matrix that sends cos theta sine theta to cos theta cos phi minus sine theta sine phi.
You didn't do that twice.
Sorry? Thank you. Sine theta sine phi. Thank you. And we're just smiling, you're just killing me. These are ugly coses, by the way. Cos theta, theta cos phi. And then we wanted to send it to sine theta cos phi plus sine phi cos theta. And the matrix that's going to do this is, I'm going to look at this and say, here I need a cos theta and a cos phi, and a negative sine theta sine phi. So I'm going to have to have here cos phi negative sine theta, or negative sine phi. Thank you. And here I'm sending cos theta. What's multiplying the cos theta? A sine phi. So I need a sine phi. And what's multiplying the sine theta? It's a cos phi. And that is my matrix of a rotation by phi. And I won't get into the details, but you can check that this works using either the difference formulas for cos and sine, or the fact that sine is odd and cos is even. But if it's a negative angle, remember when we rotate counterclockwise, this is positive, and when we rotate clockwise, it's negative. So this would be rotation by phi, this would be rotation by negative phi. And also notice that this means that every rotation matrix is invertible, because you can rotate it by the negative angle, right? So if I say rotation by theta composed with rotation by negative theta is equal to rotation by negative theta composed with rotation by theta, which is the identity. And the same thing if I'm going to write F for flipping something. Actually, this flipping it by X, or by anything actually composed with flipping it by that same thing, is always the identity. Reflection puts it back, right? Because the reflection doesn't have the direction specified. A rotation, it's either clockwise or counterclockwise, depending on the sign of the angle. But, so both of these are invertible transformations, of course. And we have found the matrices of these things. And so the final step is we're going to put this together and find the matrix that flips a line. Bless you. That one was... Even a broken clock is right twice a day. Okay. So, the next one is this matrix. I want to flip, this is y is equal to mx, and I have a vector that I want to flip across this thing. And the way that I'm going to think of this is not, I don't know how to flip it across this line, but I do know, I'm going to know the line, the angle here, theta, that this line makes with the positive x-axis. And the way that I'm going to approach this is, instead of trying to flip it across y, I know how to flip it across the x-axis, and I know how to rotate it by theta. So I'm going to rotate it by theta. That's going to bring, I'm not actually rotating the line, but that would bring it to the x-axis. It would put it in the position of the x-axis. So this would put this line in the position where if I flip it across the x-axis and then bring it back up by theta, that will be the equivalent of flipping it across the line. Right, is that clear to everyone?
Can you say that one?
Yeah.
So this theta is the angle that the line makes.
Yes.
So if I were to rotate this line down by theta, it would lie along the x-axis.
Yeah.
So if I rotated this vector down by that same theta, by negative theta, it would preserve the distance between it. You can think of it as bringing them both down and then flipping it and bringing them both back up,
Okay.
even though we're actually only bringing this one down, right? So what this is going to be is first a rotation. I'll write it. Rotation by negative theta and then flip it along the x-axis, and then a rotation by theta to bring it back up.
Is that like, would you do the composed? Is that what?
Yeah, we're gonna, composed, sorry, thank
No,
you.
I just don't know the notation. So.
Yeah, just one after the other, right? And this actually is gonna be equivalent to multiplying the matrices of these transforms. We haven't proved that matrix multiplication is composition of functions, but it is.
Okay.
Composition of linear transformations, but it is. And we'll do that in the connecting the dots sessions. Eventually, after this storm of the midterm is over. After the midterm storm, after we weathered the midterm storm. Okay, so how are we gonna make these matrices? Well, first I need the rotation by theta matrix, right? And we've seen that this is cosine theta, negative sine theta, cosine theta. And then I'm gonna reflect it across the x-axis, right? And this, of course, is 1, 0, 0, negative 1.
So if you did r theta first, then you would flip it across the y-axis? Like if you did r theta, no, not necessarily, never mind, because it's measured to the positive x. Oh.
Yes, so we can do that in a different, yeah.
Okay.
But good thinking, though. You should always be thinking about stuff like that, like what if I did it the other way, and yeah, wonderful. I always love to see students do that. Okay, so, and then rotation by negative theta is just I plug negative theta in. All it does is switch the sign of this sign. And that's because sine is an odd function, and cosine is an even function. Cosine is symmetrical around, it displays symmetry around the y-axis. So it's even, and sine is symmetrical around the line y is equal to x, so it's odd. Although we won't get into that too much. But the way I'm going to simplify this for the purpose of these computations is I'm just going to replace the sines with s's and the coses with c's. And they do this in the book as well for this proof. So there's a correspondence between that. So this gives me c s negative s c times 1, 0, 0, negative 1. This is c s negative s c. And what does this give me? Well, this one turns into c negative s negative c. And then I'm multiplying this by c s negative s c. And this gives me c squared minus s squared.
Which is,
Yeah? Yeah, c squared minus s squared. Negative cs, negative cs, negative cs. So this is, yeah, negative 2. Shouldn't it be positive though? I feel like I've done something silly. This was negative s, s, c, c. I got c, negative s, negative c. This should be right. Okay, let's just keep going with this. If I've done something silly, just look at the formula in the book. But this gives you the process of how to do it. This gives me negative c, negative 2cs. And then the last one is s squared minus c squared. Maybe the silly thing I'm doing is thinking that I did something silly. I don't know. Okay, we end up with this. I'm pretty sure this should be 2cs.
not negative.
Yeah, but I don't know why. I'm just going to keep going with this. And at the end, we'll probably see that it should be. But the whole point is the process of how we get here. Because there is the formula in the book that you can just look at. But yeah, I am under-caffeinated at the moment. So we get this. And now all that's left to do is we were given the matrix. We're trying to find the matrix that flips it along the line y is equal to mx, right? And we weren't given the cos and the sine, we were given the slope m. So we need to get it in terms of the slope, not the cosines and sines. So how are we going to do this?
Draw a triangle.
Yeah, we're going to be clever. We're going to draw a clever triangle. We're going to take multiply y is equal to mx, and I'm gonna go 1 across, this is theta, and this means that because this is the rise over the run, this will have to be m, and this will be root 1 plus m squared, right? And now I can get cosine theta is equal to 1 over root 1 plus m squared. This board does not erase properly. And sine of theta is equal to m over root 1 plus m squared. And yeah, I'm positive this is supposed to be positive at this point. Yeah, this is totally supposed to be positive. I don't know what went wrong, but it's supposed to be positive. And the signage on this might be screwed up as well. So look in the book for the actual formula, but this is the process. Okay, so now we're going to substitute this in, right? Because this is our S, this is our C. And so we put here, this is going to be 2 times C times S is just going to be M over, because we're multiplying both roots, it's 1 plus M squared. This is going to be 1 squared minus M squared. So 1 minus M squared over 1 plus M squared, although again, I think the signs might be messed up in these. I don't know. This is going to turn into M 1 plus M squared, and this will be M squared minus 1 over 1 plus M squared. And again, I'm pretty sure these are actually flipped, but again, process. This turns into, I'll put it this way, 1 over 1 plus M squared, 1 minus M squared, 2M, 1 plus M squared. And I think for the next thing, we'll look up one of the problems that involves this, and then double check the formula, which I'm pretty sure is off by a minus sign here, and then use that to actually do the problem.
Yeah, that bottom one should be m squared minus 1, right?
Should it?
Yeah.
Dude, can you check the formula quick?
Yeah, sure.
And then we'll find that problem.
Charging for what?
My laptop.
Do you have a laptop charger?
Yeah, 1 minus m squared minus 1.
1 minus m squared minus 1.
Mm-hmm.
Okay, so that's the final thing.
Yeah.
So now, okay, actually, in that case, we can just suppose.
Yeah,
I
you
have-
had that. What did you do? Like,
I
look
had
at the
that.
other one.
But you have a 2.
Yeah,
Then it's 2m, right?
yeah. Why do you have an m there?
Oh, I had it right?
You had it right, except there should have been a 2m and a 2m.
Where is the 2 and something?
It is supposed to be 2m, 2m.
I don't, it is, no, we have the right thing. And the idea is that like people watching the video and all you guys should derive it for yourselves and not make whatever little computational mistake I made, and then get that, because that's how you remember it, or you can memorize it for the test. But the thing is, I want to show an example. So if they ask me to show, I think this is the exact one from the problem. The matrix, I think this is one of the problems. It said show that this matrix is a reflection across a line, and it was 1 over 5, negative 3, 3, 4, 4, or it was like negative 3 over 5, 4 over 5, 4 over 5, 3 over 5. Can anyone tell me what this is the matrix of?
Reflection about y equals 2x.
A 3, 4, 5 triangle.
3, 4, 5 triangle?
Well, because you can get to, if you have like it's all the hypotenuse is 5.
3, 4, 5 special triangle.
It's special triangle. The hypotenuse is 5, and it's
Pythagorean triple.
yeah. Cos theta,
Well, no.
sine theta, sine theta, cos
No, it's a
theta.
reflection of matrix, though. They give you that in the question. If it was
Yeah,
supposed to be a
but
sine theta, that would
I think I know what you're talking about.
Yeah.
Mhm.
And again, that is wonderful that you're thinking.
That's cool.
And the things that are connected. But yeah, this is, and the line, the reflection across line y is equal to 2x. Because we factor this out, we see this is 1/5 times 1 minus 2 squared, 2 times 2, 2 times 2, 2 squared minus 1. And that's how we would like apply this on a,
You lost.
so this is just,
Factor
the
out
2 is the m here, so I factored out the
Oh, I see.
1/5.
I see.
Oh, sorry, and this is 1 plus 2 squared, right? Yeah.
What
Okay.
was the original question that they asked?
It was to show that this matrix is a reflection matrix, or find out what this is the matrix of.
I see.
And that, I think, is a good place to kind of